Hello class, welcome to our video notes on Skill 4 from Unit 2B, where we are now going to put to use all of that new vocab we learned. So, just as a quick reminder, I have a couple images here of the power functions that we were observing in class on Friday. If you recall, when the parent functions have odd powers, okay, so these are the graphs of all of the parent functions with odd powers. This is x to the first. This one here was x cubed. This red one was x to the fifth. And then this hard to see blue one was x to the seventh. What we noticed is that the ends, okay, when you look at the ends of each graph, they were all going in opposite directions, okay? On the right side, as x was going to the right, the ends of these graphs were going up. We say the y values were approaching positive infinity. But on the left side, they were approaching negative infinity. They were all pointing down. So the ends, the right end and the left ends of the graphs, are going in opposite directions. That's the main thing we noticed about odd parent functions. The other thing that we noticed is that for the powers of 3, 5, and 7, the graphs all have the same basic shape. They all kind of look like this sort of squiggly graph, right? We learned how to graph the x cubed graph, and we learned why it looks like this. Well, it turns out x to the fifth and x to the seventh look very similar. They're just a little bit skinnier because their powers are higher, but otherwise they have that same odd degree squiggle. Now, the x to the first didn't have the squiggle graph, but it does have the same end behavior, which is going in the opposite directions. Positive infinity on the right and negative infinity on the left. Okay, now our even power functions, well, those graphs, so here we have the graph, this one here is the graph of x squared. This one's x to the fourth, that one's x to the sixth, and the skinny one here on the inside was x to the eighth. Well, you can see from these graphs, they all had the shape of a parabola. They all had that symmetry across the y-axis and that turning point right at the origin. And so those ends on the right and left point up. They all pointed up. Positive infinity on the right and also, again, positive infinity on the left. So we just noticed that the ends of these graphs were pointing in the same direction. Now, one thing we didn't get to in class on Friday is talking about what would happen if the leading coefficient of these graphs was negative. See, the equations now are all 1x to the first, 1x cubed, 1x to the fifth, or 1x squared, 1x to the fourth, 1x to the eighth, etc. So these all had a values of 1, right? These all had leading coefficients of positive 1. And so the end behavior was also taking that into account. So then the question is, well, what would happen if the a value was negative 1 or any other negative number? Well, if you recall from our transformation rules, negative leading coefficients cause the graph to vertically reflect, over the x-axis. So these odd degree ones, all these y values here on the right that are currently positive because the a value is positive, these would all become negative should the a value or the leading coefficient be negative, so they would reflect down this way. Okay, so an a value of negative 1 would cause that vertical reflection. And then on the left, it would also reflect it, but it would reflect it up. So the graph would still have opposite end behaviors, but they would just be flipped around. So on the right, the end behavior would be pointing down, and then on the left, it'd be going up. Now over here for these even degrees, if you're dealing with a negative leading coefficient, again, you get that same x-axis reflection. It would flip these positive y values across the x-axis, over the x-axis, and make them all face down. So they would look like a parabola opening down. So they still have, like, each side of the graph still has the same end behavior, but instead of both pointing up, like when the leading coefficient was positive, they both point down because now the leading coefficient's negative. So this, we're going to use this, we're going to generalize this. This will also be the same for the end behavior for any polynomial that has either even degree or odd degree. We can generalize. Now the middles of the graph will bounce around a lot more. when you start adding more things to the polynomial. But the end behavior will behave the same. So let's summarize that one more time. We're going to draw a little graph in here. So the graph I'm drawing here is the graph of a general even degree with a positive a value. Basically, those look like parabolas opening up, right? Just like all these graphs over here. They were all even degreed with a positive a value. Now, sometimes, even when we add more variety to the equation and then maybe the graph gets more complicated, sometimes there might be more turning points going on in there. But the end behaviors will still be the same. Both arrows on the right end and on the left end will be pointing up. Both ends point up. So we say we say it this way. For the right end, x is going to positive infinity. Well, the function is going up, so the y value is also approaching positive infinity. Now for the left end, that's when x is approaching negative infinity. The y values are still going up, so y is still approaching positive infinity. So these are the same, right? Same. So when you have an even degree, you will have same end behaviors. If the a value is positive, both ends are pointing up. Now, we looked briefly at when the a value is negative. It basically takes that parabola and makes it face down. So generally it will look something like this, right? Both arrows are pointing down, but even if the graph has more variation to it than that, and there might be some more squiggles going on in there, there could be 2, 3, 4 turning points. So lots of bouncing around in the middle, but for end behavior, we block all of that out. We block all of that out, and we just look at the ends. They still point in the same direction. That's the key. They point in the same direction. So we say this, x going to positive infinity. Well, if the a value is negative, then the y values will go down to negative infinity. And the same will be true on the left. As x goes to the left, the y values still drop down to negative infinity because it was an even degree, so the end behaviors on the right and left will be the same. So I want you to always put these ideas together. Even degree, same end behavior. Okay? We can kind of picture this squiggly shape, right? Odd degree functions have this squiggly shape. So the ends are facing opposite directions. Now, when the a value is positive, that's this first category, it looks like these here, all these ones that I had graphed. X to the third, x to the fifth, x to the seventh. It goes up on the right and down on the left, okay? And again, even if there was more variation, more like squiggling going on, boom, boom, boom. If we ignore all that middle bouncing around and just look at the ends, what we notice is they go up on the right and down on the left. They go in opposite directions. On the right side, y goes up for a positive a value, odd degree function. And on the left side, y goes down for a positive odd degree function. The end behaviors for y are opposite, right? When the degree is odd, the function will point in opposite directions. Okay, now if the a value happens to be negative, then it will take this squiggly shape and reflect it over the x-axis, which kind of flip-flops it and just has it going the other direction. It flip-flops that graph. And again, even if I added more variation to it, so there's all these like squigglies going on in the middle, lots of bouncing around up and down in the middle, we ignore the middle when we're talking about end behavior and we just look at the ends. And notice on the left, these graphs both point up. On the right, they both point down. So in notation words, we would say x goes to infinity. Y is actually going to negative infinity on the right, right? Down here, it's going to negative infinity. X going to negative infinity on the left makes y go to positive infinity. And again, since the degree for this was opposite, these end behaviors over here, the degree was odd, The degree for this was odd, so the end behaviors will be opposite. The arrows on the graphs will be pointing in opposite directions. So that is what we are going to use to determine the end behavior of the graph. That's just the end, right? We do still have to figure out sort of what the middle would be. So that's where steps 2 and 3 come in handy. So step 1 is just kind of taking a look at the degree and then whether or not the leading coefficient is positive or negative, and that'll tell you where the ends of your graph will be pointing, which is super helpful. But in step 2, it has us find the zeros, find the x-intercepts. That helps us understand maybe more what's going on in the middle. You know, where does it hit x? How many times does it have to bounce around over the x-axis? So basically to do that, we're going to, if it's already factored, we're just going to set each factor equal to 0 to find them. If it's not already factored, we're going to have to factor it and then set each factor equal to 0 to find those x-intercepts. The other thing that we will do is we'll find the Y-intercept, because that helps us kind of figure out a middle point there, something in the middle, just to help us get a better idea for the graph. We're going to plot all those points. We're going to use our end behavior to kind of figure out the overall shape, and that's how we're going to sketch these graphs. So let's give it a try with example 1. So here in example 1, I actually wanted to start off with a quadratic, something that is a second degree. And you might be wondering, Ms. Lasner, how do you know this is a second degree? It's because I have 2 factors that are both to the first power. So if I FOIL them out, which I'm not going to do right now because that takes time, but I know that if I had to multiply, if I FOILed it out, I would have to at some point multiply x times x. Okay, so I know that my term with the highest exponent would be 1x squared. The 1 is coming from the fact that there's an a value of 1 out here. So when we don't have a number written, we understand that these parentheses are being multiplied by 1. So that would be my leading coefficient. So this is going to be a quadratic. So I'm going to do all the steps as listed here in the table. I'm going to find end behavior, right? I'm going to determine that. I'm going to find the zeros. I'm going to find the y-intercept. But there's one additional thing I'm going to find with this one because it's quadratic, and that's the vertex. That's just going to be a nice review of our past unit. Okay, so for the end behavior, the first thing I noticed was how many factors there are. That'll help me figure out what the degree is going to be without having to FOIL it all out. You just look at how many factors you have and you just make a note that's how many times x would get multiplied to itself at some point. So the highest power for this will be 2. And then you also want to look in front of the x's. There's like a 1 in front of all of them and then a 1 outside the parentheses. That tells me that my a value is going to be 1, which is positive. So the fact that my degree is even, it's 2, right? And my a value is positive, that tells me that the ends of this graph are going to both point up. Of course, we knew that because it's a quadratic, so we knew that the graph would look like a parabola, you know, something like this. But still, I wanted to kind of show you how we can use the end behavior to also determine that. If the degree is even, the a value is positive, both ends will face up. Okay, so that's step 1. Step 1 was finding the end behavior. Step 2 will be to find the x-intercepts. So to do that, now this one's already factored. This is in what's called intercept form, which is super nice. We just have to take each of those factors and set them equal to 0 to find the x-intercepts. And then from there, it's a nice, quick, simple process. I'm going to have one at x equals 5 and the other one at x equals negative 9. Okay, so those are my 2 x-intercepts, and each of those occurs only once. So I'm going to plot those points. One at positive 5 and one at negative 9. Okay, so I've got my x-intercepts. And then I'm going to do the third step, which is to find the y-intercept. And that I find by just plugging in 0 for x. And so in this case, it'll be -5 times +9, which is -45. So it's quite low, which means if I want to include that on my graph, I'm going to need to scale my y-axis appropriately. So we'll do that in a moment. Okay, now here's the extra thing that I'm adding for this one because it's quadratic and we have enough tools to be able to find it, and that is the vertex. Because here's what we know about a quadratic. It has symmetry. It has what's called axis of symmetry, meaning that there's a middle to it, and every point on the right and left is equal distant from the middle. So I know if I have an intercept at -9 and at 5, if I find the middle of those points, that will help me find my vertex. So to find the middle of those points, I'm just going to average them. So that's 5 plus -9 over 2. I'm just taking the average of 5 and -9 to find the middle, and I locate it at -2. So this dotted line here is my axis of symmetry, right? Something we know about quadratics. It locates the middle. And then if I want to find the rest of the vertex, so this was the x coordinate of the vertex, okay, x equals -2. To find y, I just need to substitute -2 in the equation where x was. And then I get -7 times 7, that's -49. If I put these two values together, that gives me 1 point on the graph, which is my vertex. So we're not going to be able to find this for the higher degree polynomials at this point, but at an Algebra 2 level, we are able to find the vertex for a quadratic, so might as well go ahead and use that. Okay, so I notice I have to have my y values go all the way to at least -49 on this graph, so I think what I'm going to do is have my y-axis go by 5s. And I'm going to make a note of that, like right here. Just going to have it go by 5s along my y-axis so that I can reach this value. So -45 would be, let's see, 5, 10, 15, 20, 25, 30, 35, 40, 45 right there. That's my y-intercept. And then my vertex is down at -49, so maybe like right here. But at the x value of -2, okay? One other thing, I'm going to throw this in there too, because one other thing we learned last unit is that every point on one side of the vertex can be reflected to the other side. Not only the x-intercepts, but the y-intercept as well. So now I have a lot of nice points, and I can go ahead and connect them and form the shape of my parabola. And I knew that both of my ends would be pointing up, so they are. And so there you go. There's our graph. For the remaining polynomials, we won't need to be as specific, but when we know something about a polynomial and we know a lot about quadratics, it's great to use every tool we have to get as accurate of a graph as possible. Moving on to example 2 and 3, you can see that these are clearly going to be not quadratic. They're going to be more complicated than a quadratic because they have more than 2 factors. And so we're going to stick to just the 3 items listed in the steps: the end behavior, the x-intercepts, and the y-intercept. So let's just start by trying to figure out the end behavior of this equation that we see here in number 2. So let me just point something out to you. One of these factors here is squared. And so what we have is x times x minus 1 times x minus 1 again times x plus 8. So technically, this equation here has 4 factors. What that tells me is that if I were to FOIL it out, which I'm not going to because that would take a lot of time, but I know that at some point I would have had to multiply x times x times x times x. At some point, all 4 of these x's would get multiplied to each other, which tells me that the highest power x will reach is 4, because there are 4 x's that at some point would get multiplied together. So that tells me that my degree is 4, which is even. Okay. Then I look in front of all the x's, right? There's 1's in front of all of them. So that tells me that my a value is 1, which is positive. So like example 2, like example 1, the end behavior on example 2 will also both be pointing up. Both ends of this graph are going to face up since the degree is even and the leading coefficient is positive. Okay, second thing I'm going to do will be to find the x-intercepts. Again, I'm so happy that this example is in factored form or intercept form, because then all I have to do is take each of those factors, set them equal to 0, and solve for x. And yes, I know that technically there's 2 factors of x minus 1, but I know that they would each have the same solution, so I'll just set one of them equal to 0 and find that I'll have 2 x-intercepts of 1. And then I'll have one x-intercept of -8, and then over here, one x-intercept of 0. So maybe we'll just make a little note to ourselves right here. This intercept happened twice. So this is going to be a special one. Because when an x-intercept repeats itself an even number of times, then rather than crossing through the x-axis at x equals 1, this graph will bounce off. It'll bounce off the x-axis at x equals 1. So let's take a look. So we have an x-intercept of 0, an x-intercept of 1, and an x-intercept of -8. All right, so let me see here. Oh, and one other thing I wanted to do before I try to connect everything is find the y-intercept, okay? Y-intercept we find by plugging in 0 for x. So it'd be 0 times 0 minus 1 squared times 0 plus 8, and then all of that is just going to be 0 because this one factor was 0, and it's going to make all of it just go to 0. 0 times 1 times 8 is 0. So the y-intercept is also 0. This guy here is both the x and the y-intercept. So now I'm just going to kind of starting up here because I know it has to point up on the left. And then it must come down. It has to cross through at 0, come down and bounce off at 1. And it must look something like that. I know because both ends have to point up. I know it has to cross through the x-axis at -8 and 0 because those zeros appeared only once. And I know it has to bounce off the x-axis at x equals 1 because that 0 occurred twice. Now, you're always welcome, by the way, to just plug these into Desmos and just see what happens. Because you'll notice, well, I wasn't very accurate with these turning points, right? I don't know where they go. I don't know how low this one goes. I don't know how high that one goes. So Desmos would be a place for you to see how accurate this sketch is, or perhaps how inaccurate. But at any rate, this is a pretty decent sketch of this graph, even just using these 3 pieces of information. Okay, let's take a look at example 3. So example 3 is very similar. It's given to me in intercept form, which is my favorite because all the factoring work is done, thank goodness. And I notice that, so first thing I'm going to do is look for end behavior. That's the first thing I'm going to ask you to do is look for the end behavior. And so in doing that, I notice it has 3 factors, all to the first power. 1, 2, 3. What that tells me is, if I were to FOIL it out, which I'm not going to because that would be long and tiring, but if I were to FOIL it out, at some point I'd have to do x times x times x. Each of these x's would get multiplied to each other, causing there to be an x to the third, a term with x to the third, and that would be the most x's at one time, so this will be our highest exponent. So the degree for this is 3, which is odd. The other thing that I notice is that this time there is a coefficient in front of these factors, and that coefficient is -1. So my a value is -1, which is negative. So now my end behavior will look like, let's scroll down here, will look like this guy right here. This is what it looks like when your degree is odd and your leading coefficient is negative. The arrows are going to go up on the left, but down on the right. So that's what's going to happen with this graph here. So maybe we'll put that in as sort of like a template, okay? Up on the left, down on the right. Meanwhile, in the rest of the graph, we are going to use the x-intercepts to figure out all the bouncing around it might do in the middle. So I'm going to take each of those factors, set each of them equal to 0, and solve for x. So for this one, I get one x-intercept of -2. For this one, I get one x-intercept of -7. And for this last one, I get one x-intercept of 5. So I'm going to plot all those, -2, -7, and 5. And before I start connecting and bouncing around, the third thing I'm going to do, just to help keep this as accurate as possible, is go ahead and find that y-intercept. So I'm going to plug in 0 for x, and for all the x's, by the way. I'm going to multiply all of these things together. So I get -1 times 2 times 7 times -5. So these negatives will cancel. And that will be positive. This will become positive 70. So another rather large y-intercept. So I may want to rescale this y-axis as well. In fact, I think I'm going to have it go by tens. So that means each little tick mark is worth 10. So 10, 20, 30, 40, 50, 60, 70 would be right here. And you know what? Maybe we'll label it to make it clear to the reader that we understand that that value there is at 70. Okay, so we've kind of scaled our graph differently there. And then now I have a pretty good idea what the rest of this will do. It's going to come down, and then it's going to go up, and then it's going to come down and have that end behavior facing down on the right. Oh, darn it. Let's try that one more time. Down, up, and then down. And then I don't know, does this turning point go higher than the y-intercept? I don't know for sure. I'm just kind of following what I've seen before. So it really, at this level, it doesn't matter how high or low your turning points are. What matters is if your end behavior is pointing in the right direction, if your x-intercepts are on the right spot, and if your y-intercept is on the right spot. So I think this looks pretty darn good. But you are welcome to, and I encourage you, highly encourage you, graph it on Desmos. See what it looks like. How high does this go? Why not check it out? And then also see how accurate was this done. Was it done fairly accurately? Did we get a decent sketch? If so, it's pretty cool, right? We just used end behavior intercepts to get a pretty decent sketch of a rather complicated equation. So anyways, let's move on to our next examples. Now for example 4, the downside to this example is it's in standard form. What a bummer. Standard form means we're going to have to factor it on our own. But before we do that, let's just make a note of the degree based on the highest power and the leading coefficient, which is that number being multiplied to the x with the highest power. So we can see really quick before we multiply out that the degree is 4, which is even. Okay. And the leading coefficient, the LC, is -2, which is negative. Okay, so we put those two ideas together. Even degree with a negative coefficient, that's the time when both of the ends point down, right? Because even degrees, the arrows both go in the same direction. And if it's a negative direction, those suckers are pointing down. Okay, got that handled, right? That was end behavior. So that is kind of the one upside of having something in standard form, is it's really easy to quickly pick out the degree and the leading coefficient. So that was nice. So we know both ends are going to point down. The downside is to find the zeros, we have to do all the factoring ourselves. So if you go back up to these 3 terms here, we can see that they all have x's. And actually, they all have at least 2 x's. Right? So there's a GCF of x squared that I can pull out. And when I do, actually, wait, hold up. See how my leading term is negative? Let me tell you, factoring is going to be so much easier if we pull that negative out too, actually. I just realized, because the leading term was negative. That is hard to factor. So let's pull that sucker out. And then that leading term is now 2x squared. The middle term is now -3x, and the final term is now -20. So I basically changed the signs of all 3, and then each of the powers of x went down by 2. Okay, so I know one of my factors is negative x squared. To get the other two factors, I'm going to have to remember how to factor a second degree trinomial. So quick recap. You take the a and the c, you multiply them together, you take the b value, and you have to find two numbers that multiply to negative 40 and add to negative 3. Think about it. Factors of 40. One's going to have to be positive, one's going to have to be negative, so really they're subtracting down to negative 3, negative 8, and 5. Okay, so then I split my negative 3 up into those numbers, negative 8 and 5. I group the first two and the last two. And I'm going to take a GCF out of each of those. So from 2x squared and 8x, I can take a 2x out. And from 5x and 20, I can take a 5 out. And then now I notice I have a common binomial factor of x minus 4. Love it when that happens. So we take that out as well. And then I've got 2x plus 5. Whew, that was a lot of work. I'm tired. See, isn't it nice when it's already given in this form? So nice. Anyhow, now that we factored it, all that work, I can look at this and go, I have got technically four factors, right? Because x squared could be counted twice, or it is counted twice. So this is really like saying negative x times x. And then I've got that times x minus 4, and then I've got that times 2x plus 5. So I've got 1, 2, 3, 4 factors. So to find the x-intercepts, I just set each of those factors equal to 0, and then I solve for x. Okay, so, well, this one's done. And let's make a note, that came from x squared, right? There were two of those, 1, 2. So there's actually two of these intercepts at 0. So it's a 0 with what we call an even multiplicity. It happened twice, okay? Even multiplicity. So when I graph this equation, it's gonna bounce off the x-axis at x equals 0. Okay. And then meanwhile, this factor produces an x-intercept of 4, and then this factor produces, wait for it, there it is, an x-intercept of negative 5 halves, or you could think of that as negative 2.5, whatever floats your boat. So now, let's come back to our graph. Okay, I've got two intercepts at 0, one intercept at 4, and my third intercept at negative 2.5. And, Y-intercept. Let's do that. Let's squeeze that in right here. Y-intercept. Although maybe some of you are thinking, well, Miss Lasner, we don't really need to do that. We know it's 0. Because if it hits the x-axis at 0, that's right where the x and y-axis meet. So that's where it'll hit the y-axis. And I would say, you're right, but let me just show this to you anyways. It always is good to have some reinforcement. So I'm going to plug in 0 for all the x's. And okay, so every term had an x. So if you plug in 0 for x, every term just goes to 0. 0, 0, 0, everything's just 0. Our y-intercept is 0. Okay, so now we put it all together. Graph starts down here, right? Let me erase this one here. It's too far over there. But I have the idea, right? It starts down here, and then it's going to have to go up. It's going to bounce at 0. It's going to go up and down. Something like that, right? Again, I don't know how high these turning points go, so you can check that on Desmos if you want, but I think this is a pretty decent sketch of this graph, of the shape of this graph. The main thing, again, I'm looking for is if you have the ends pointing in the right directions, if the graph is crossing x at the right spot, or bouncing where it's supposed to bounce. And the reason it's bouncing right here at 0 is because that factor occurred twice, so that solution technically counts twice. Okay, over here at example 5. same bummer, is we're going to have to do all the factoring work, right? Because it was given to us in standard form. But before we do all the work to factor it, let's just take a look at the end behavior. So I look at the highest power, which is easy to spot when it's factored out, or when it's multiplied out, when it's in standard form. You can spot that highest power. So the degree is 3, which is odd. Okay, so we know that the ends are going to be pointing in opposite directions. I can also see the leading coefficient of that term is 1. So A is 1, which is positive. So that means it'll be going up on the right side and down on the left side. It'll look like a parent graph for x to the third. Okay, on the ends anyways. The ends will look like the parent graph of x to the third. Okay, so we got the end behavior down. Now comes the task of finding the x-intercepts, which requires factoring in this case. And since there are 4 terms, 1, 2, 3, 4, we are going to do what's called factor by grouping. Okay, factor by grouping. So that is where you group the first 2 terms together, x cubed plus 2x squared, write a plus sign between, and then group the last 2 terms. And then we're going to go ahead and take the GCFs, GCFs of each of these terms, and we're going to pull them out. So this one I can take out a GCF of x squared, leaves me with x plus 2. This one I can take out a GCF of negative 5, leaves me with x plus group the second pair of terms. So I have negative 25x minus 50. Then I look for the GCF of the first 2 terms and factor that out. So that's x squared, and I get x plus 2 left over. Then I look for the GCF of the last 2 terms, which is negative 5, and I get positive x and positive 2 from that pair. And then what I notice from there is I have now a common binomial, right? That's the sign I'm doing it right. So I will factor out that binomial. So I'll take an x plus 2 from this part and also that part. And then I'm left with an x squared from the first part and a minus 5 from the second part. Oh my goodness, what am I saying? Oh goodness, this is not 5. This would be 25. Sorry, 25 is the GCF between 25 and 50, which I think I had in my head because 25 divided by 5 isn't 1. And 50 divided by 5 is not 2. This should have been a 25 right there. Just kidding. Okay, so minus 25, and then same here, minus 25. Okay. Now that we're on track here, now I notice this guy, this little stinker, these difference of squares, right? They like to hide inside other factoring problems so that you don't notice them. But we need to always be on the lookout. So the difference of squares here is x squared minus 25, and it can factor further. It can factor into x plus 5 and x minus 5. Okay, so these are the 3 factors of this polynomial. Now how that's helpful is that can help us find the x-intercepts. So that's what we're going to do, is find the x-intercepts by setting each of those factors equal to 0 and solving for x. So I will find each of my x-intercepts. So I've got one at negative 2. I've got one at negative 5, and spoiler alert, one at positive 5. 3 single intercepts, so the graph will cross right through the x-axis at each one. It's not going to bounce at any of them because none of them repeated themselves. Okay, so, and then let's find the y-intercept as well, and then I'll start plotting these points. So the y-intercept is what you get when you plug in 0 for x. So I'm actually going to use the standard form version to do that, the one way up here, because I can see that the first 3 terms all have an x. So I know that if I plug 0 in for those x's, they'll all go to 0, and then I'll just be left with negative 50. But I'll show you here as well. 0 cubed plus 2 times 0 squared minus 25 times 0 minus 50. That goes to 0, that goes to 0, that goes to 0, and whoosh, I'm left with negative 50. Another gigantic y-intercept, so we'll have to scale our y-axis appropriately. Again, let's have it go by tens again. So let's see, 10, 20, 30, 40, 50, so that'd be like right there. I'll just have the x-axis go by ones. So it's -2, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. And then we use our end behavior. It's going to go up, and then down, and then up. Something like that, right? You can check it on Desmos, but that's pretty good. I'm willing to wager that that's pretty good. Anyhow, these are the tools we use, right? End behavior, X intercepts, Y intercepts. And we can get some pretty decent sketches of some pretty complicated graphs. So you got some pretty powerful tools at your disposal now. And I look forward to helping you use all of them in class on Monday. I'll see you then.